So there's a few that look like almost the right answer, but without bothering to convert units, you have to put the units in meters. The radius has to be in meters. So the way to solve this one, what you're looking for is a normal force such that you have the equivalent of 1g acceleration continuously. And so to do that, you use a sub c equals 1g. This is equivalent to f sub n is m a sub c, because the normal force is your centripetal force. All right, and so a sub c is omega squared r, therefore omega is square root a sub c over r, which is 9.8 meters per second squared, divided by 2,500 meters, because 2.5 kilometers is 2,500 meters. So when you put all that into your calculator, you get 0.06 roughly plus. All right. So, today we're going to talk a bit about the one concept in rotation that we haven't made it to yet, which is a pretty important one. This is what's called angular momentum. Angular momentum, I'll write the definition up here for you in the equation form. We usually use an L to represent orbital angular momentum, or angular momentum classically in general. So it's a vector, and it's defined as r cross p. It's basically the radius at which the orbit is happening crossed with the linear momentum. So if you have something that's in a circular orbit, for example, here's the center of the circle. Your object is out here, completing a circular orbit like so. This vector right here represents r. It's the instantaneous vector that runs from center to where the object is. And then this one right here the linear momentum, you'll recall, is defined as mass times velocity. You have an object of mass m, it's moving instantaneously at velocity v. This gives us our angular momentum. All right. Now some things about angular momentum. First of all, what is the magnitude of the angular momentum going to be? Well, it's going to be given by r times p times the sine of the angle between the two of them. So at a right angle, that sine term goes away, or is equal to 1. All right. So this is sometimes memorable as mrv sine phi, or mrv. I reorganized the letters slightly because it's just somehow more memorable to remember Mr. V than RMV. But it doesn't matter. Put them in whatever order helps you remember. So that's your magnitude. Now, you can also notice that for this point object, if it's moving around the circle, it has some angular speed omega, and that omega would be v over r. Right? Or likewise, that v is equal to omega times r. So this right here is also equal to m r omega sine phi. So this is r squared. And mr squared, what is that? For this uniform circular motion, the sine theta term actually goes away, for what it's worth, because it's equal to 1 at all points on the circle. What is mr squared equal to for a point object? What's that? Moment of inertia. Okay, so this is equal to I times omega. All right? So that's the magnitude. The magnitude, depending on what you're given, is r times p times sine of phi, or it's mrv, or it's I times omega. What about the direction of this thing? How do we get the direction for the angular momentum? Well, how did we find direction the last time we did a cross product? Does anybody remember what the last time we did a cross product was? It was torque, that's right. Torque, I'll write it over here, torque. Was R cross F. And we found that by doing R times F times sine of the angle between the two of them, similar to what we've done here. Now, how did we find the direction for torque? With the hand. Yeah, with your right hand. Your right hand. All right, so we want the right hand rule. And it's the same right hand rule that we learned over here with torque. You take your fingers, you point them along R, then you curl them to point along P. Your thumb gives you the direction of the angular momentum. So in this particular drawing's case, the angular momentum is out of the board at you. If it was moving in this direction, it would be into the board, away from you. All right, so this one right here, we might represent L as having this vector direction, or we might say that it is counterclockwise. Is sort of the positive direction in general. If it was, we had this thing moving in the other direction, maybe we have another one that's here somewhere. Then this one would be said to be moving into the board or clockwise. So that gives us our magnitude and our direction for angular momentum in general. And so now we might ask what we can do with angular momentum, what it can be used for. And what it can be used for actually spills over into next class, because one thing it can be used for is figuring out collisions between extended bodies. So that will be Wednesday's class. That's the next class that we will meet. Right? Monday's a holiday, so no class Monday. So Wednesday we will talk about collisions between extended objects. Today we want to consider some of the other uses, the ones that don't involve collisions. All right. One of them, a simple use of it, making use of I times omega, you can find in stuff like figure skating or other types of sports where you need to be able to spin, high dives and that kind of thing. How does a figure skater spin up? And the answer is they usually start, in some pose like this, and they start spinning slowly, and then they bring their arms in close, and they suddenly speed up when they do this. That's an example of what's called conservation of angular momentum. It turns out that, like with linear momentum, angular momentum is also conserved. And I'll give you the condition for that, because it has everything to do with torque. All right, so recall, for linear momentum, sum of forces was delta P over delta T. It's the change in your linear momentum per unit time. So if you wanted to change linear momentum, you needed to apply a net force to the object for some amount of time. For angular momentum, the law says sum of torques is change in angular momentum per unit time. All right. So now let's revisit this ice skater. Right? They start off, they kind of have like their arms out and they're like spinning very slowly on the ice. And then they draw in their arms and the spinning gets faster and faster, and then they kind of slow down by putting the arms back out. Now, why does this happen? Well, there is very little torque. There is a little bit, but there's very little torque on the ice skater while he or she is spinning on the ice. Where does the torque come from? There's two sources, really. There's air resistance, which is usually quite negligible at low speeds. And there's friction with the ice, which is probably also pretty close to negligible because it's ice. The point of ice skates is that they want to have very low coefficient of friction with the ice. All right, so torque is almost zero in this case. Now, what happens when the ice skater starts like this and then brings the arms in like this? What has the ice skater changed? The air resistance will go down. That is true. But it won't go down much because it was really low to begin with. The ice skater changed one other thing besides the air resistance. Sorry? Radius? Okay. Yeah, so some mass was originally like way out here at a big radius. You bring the arms in. The radius for this much mass has gone down quite dramatically. If radius changes, what does that mean has also changed? The angular momentum is conserved. That one did not change. Omega will change, but this is in response to the thing that radius changes. We just talked about it. Oh, yeah, there we go. Somebody said it. Yeah, okay. Your moment of inertia changes. If you change R, you change I. Specifically, R gets smaller, so I will get bigger. If I gets bigger, R gets smaller, so I get smaller. If I get smaller, omega has to get bigger to compensate with it, because the product of I times omega must stay constant if there's no torque. In this case, there's virtually no torque. So this means that this person will spin up. All right. So there's one application. Let's consider another application. Now notice that there is a force involved in this before we do the other application. There is a force involved in this. You got a bunch of weight out here. You've pulled all that weight in like this. That requires some force. You've applied some force on the weight that's out here to bring it in closer. So you have a force, but you don't have a torque. Why is that? Because the force is entirely radial. Right? Force is entirely radial. Let's consider another example. This one is on a larger scale, but it goes more with this kind of a diagram. Planetary orbits, or any kind of celestial orbits like this. So, how did the planets orbit around the sun? What kind of orbit do they make? Is it circular? Is it hyperbolic? Is it a tangential type of orbit? No such thing, by the way. So it's not that one. What shape is the orbit? Ellipse. All right. So if you look at Kepler's laws, for example, first law says planets orbit the sun in elliptical orbits. It actually continues from there. It's not just any ellipse. How do we position the ellipse? What's that? Okay, it can be positioned at some angle. Maybe, like it could be, but that's not the main thing. The other part of Kepler's first law is that the sun is in a particular location within the ellipse. So where in the ellipse does the sun sit? It is not the center. That's right. It's actually at one of the focal points of the ellipse. All right. So implication. As the planet goes around the sun, the distance with respect to the sun does not remain constant. It gets closer and gets farther away. So what's going to happen to the planet's orbit as it gets closer or gets farther away from the sun? What's that? What is weaker or stronger?
Like gravity.
Okay, gravity gets weaker or stronger. I agree. Newton's law for universal gravitation says force of gravity is G m1 m2 over r squared. Since these three are all constants, if this gets smaller, we get more force. If this gets bigger, we get less force. So granted. It turns out that this right here was Newton's attempt at explaining, among other things, Kepler's laws. And this is part of how he did it. All right, what else happens, though? What happens specifically to the planet as it orbits around the sun? If it gets closer, what happens? Sorry? It could. Actually, we're moving closer to the sun right now. Our winter is when we're closest to the sun. Our summer is when we are farthest from the sun. And that has more to do with the tilt of the Earth, rotation relative to the plane of the orbit. It's going to be summertime in Australia soon. If you didn't know this. But yeah, I suppose it does on average maybe become a little warmer or a little cooler if it's closer or farther. So Kepler, by the way, there are 3 laws to Kepler. I'll just give all 3 of them to you. But the second law, where it comes from, is what's called the equal area and equal time law. So basically this law says during any time interval, for the entire orbit, an equal area is swept out to any other time interval, delta t. Right? So in the same amount of time as this thing goes around the orbit, the same area gets swept out. The diagram that goes for this, and I'm going to go ahead and erase a little bit because it's getting cluttered. The diagram that goes with this particular law looks something like this. Maybe you have the sun here, maybe you have your other focal point here. Your ellipse could maybe look like this, for example. So you have your planet right here. Is it moving quickly or slowly when it's in close like this? All right, maybe I erased too much. All right, this one right here says, as we get close to the star, r is small, therefore omega is small. Or if you'd like, r is small, m is the same, therefore v must be large. So we have a large value for v. So it's moving quickly here, so maybe in this time interval, delta t, it goes from here to here. Sweeps out this much area. So here's the area swept out, this is in time delta t, here's my velocity. Now we go over here where we're somewhere far away from the star. If you're far away from the star, that means that r has gotten to be big, and therefore v has gotten to be small. So now we draw, and this is a little bit of an exaggeration, but now we draw v like this. So in the same delta t, maybe it moves from here to here. Oops. And it turns out that this area and this area right here, according to Kepler's second law, must be equal if the time it took to move from here to here and the time it took to move from here to here are the same. All right. Now this is, although they didn't necessarily have angular momentum, they didn't have the law of the conservation of angular momentum formulated yet at this time. This can be obtained from the law of the conservation of angular momentum. I think your book actually does walk through the derivation for you of that. All right. If you don't want to go through the process of deriving it, you just have to remember that as you get a larger value for r, you have a smaller value for v, you move more slowly. It's sort of equivalent to saying I have two almost triangles, they're not quite triangles, but two almost triangles. V is going to tell me something about the base of the triangle, r is going to tell me something about the height of the triangle. And the area for a triangle looks like 1/2 times base times height. So if I make v large and r small, it's going to have the same effect as if I made v small and r large. All right. And angular momentum, the full derivation preserves that for you, even though it is not actually a triangle. Over short time intervals, it can certainly be approximated as a triangle, and this works. But it turns out that this law is true over longer time intervals as well. So we don't need to approximate it necessarily as a triangle other than for visualization. What's the third of the Kepler laws? Does anybody know? We don't have time for another quiz. All right, the third of Kepler's laws goes like this. Basically what it says is the square of the orbital period is proportional to the cube of the average distance between planet and star. All right, so period squared is proportional to r cubed. What this means is that t squared for first planet over t squared for second planet is r cubed for first planet over r cubed for second planet. Okay, this is Kepler's third law. Okay, and we can rearrange it if we would like. For example, we could say t squared over r cubed 1 is t squared over r cubed 2. These are the same equation, just rearranged a little bit. All right, this works out. This is Kepler's third law. He did it for planets orbiting the star. By the way, these laws were not necessarily derived. Kepler did not necessarily mathematically derive them. Instead, he made, his mentor Tycho Brahe made, many observations, both naked eye and with a telescope, over years. And they sort of tabulated, okay, where is Venus now? All right, where is Mars now? Where is Jupiter at this point? And so on. And they found that these three things fit to the orbits of all those planets. So they sort of mapped out, okay, how much area is Venus sweeping out in this month? How much did it sweep out the next month? How much the next month? And so on. Now repeat for Mars, repeat for Jupiter, and so on. Repeat for the Earth. They find that it works out nicely. I have in the video a table, and your book, I think, has a table, a different table, that tells you the mean orbital distance from the sun for each of the planets, the orbital period for each of the planets, and then it calculates the ratio, this ratio basically, t squared over r cubed, for each of the planets. It turns out that for all the planets, it's just a little bit smaller than times 10 to the minus 19 seconds squared per meter cubed. 19. Now they're not all, it turns out, exactly the same to three significant figures. There's slight differences. For example, for the Earth, it's 2.99. For Mercury, it's 2.97. For Pluto, it's about 2.99, and so on. There's little variations. Those little variations are because the planets are not necessarily making orbits that just involve the planet and the sun. There's all the other planets to consider. There are any of the moons of these planets to consider, etc. This perturbs the orbit slightly and throws things off. But over 1 month scales of time, or 1 year scales of time, etc., it's good enough. It's close enough to say this must be some sort of a law. It turns out that as with this one can be derived from conservation of angular momentum. Turns out that Kepler's third law actually can be derived considering a circular orbit using Newton's law of gravitation. So this law right here, in the light of Newton, says that t squared should be equal to 4 times pi squared divided by g divided by m. Times r cubed. Where g is your universal gravitational constant from Newton's law of gravitation. M is the mass of the star, or the thing that's being orbited in general. And then you have the mass of the planet, or the thing that is doing the orbiting, and you have your r squared. All right, so the 4 pi squared g over the 4 pi squared over gm, is basically your proportionality constant for Kepler's third law here. So we don't need to necessarily say it's a proportionality, we can say it is an equality. All right. So now let's consider an example with a planet moving in orbit around the sun. All right. A numerical example with what time we have left. Let's consider, well, we could do the Earth, for example. We know the values for the Earth. We also know the value for the mass of the sun. The sun's mass, m, comes out to 1.99, roughly, and times 10 to the 30 kilograms. All right. Now the Earth orbits around the sun. It's an elliptical orbit, but there is some such thing as a mean radius for the orbit. The mean radius for the Earth's orbit is, let's see, so, no, it's not 6, it's 1.496. Times 10 to the 11 meters. All right. Given these information, what do we expect the orbital period to be? Likewise, what is the orbital angular momentum? All right. For the orbital period, we can use Kepler's law in this form. T squared is 4 pi squared over g m r cubed. So we need to take a square root of both sides. 4 pi squared times this. And then g is 6.67 times 10 to the minus 11 Newton meters squared per per kilogram squared. And the mass of the sun is 1.991 times 10 to the 30th kilograms. So we got to plug all that stuff into a calculator. All right, 4 times, I don't know where the pi button is on this calculator, so I'll just enter it manually. 3.14 squared times 1.496, which is cubed. Divided by the 6.67, divided by the 1.991. Right. So what I have at this point is now we got to deal with the powers of 10 here. 10 to the 11th, we're cubing it. So that's 10 to the 33 minus 11 in the denominator, that's 10 to the 44, and then divided by 10 to the 30, so we have 10 to the 14. So we take a square root, and what we end up getting is about 3.153. Times 10 to the 7 seconds. That's your orbital period. Now we ask, given that this is the orbital period, what is the expected orbital period? How long is an actual orbital period of the Earth? We all know the answer to this question, by the way. It takes us 1 year. It takes us 365.249 days to go around the sun one time. And so you can convert that into seconds, and what you end up getting is 3.156 times 10 to the 7. So this digit is a little bit off. Notice, though, that I also underestimated my value of pi by calling it 3.14. And there's some other rounding errors in here. You have also to consider any perturbations from the rest of the solar system. So this is not a bad estimate, not a bad calculation. We're well within 1%. And we're within about we're within about 0.1%, 1/1000th of the actual answer. Okay. What about the angular momentum? How do we get the orbital angular momentum? We have two ways of doing this. One of them is to go out and calculate what the moment of inertia for the Earth is about the sun. You can use parallel axis theorem, but what you'll find is that the actual moment of inertia of the Earth about its own center is pretty negligible compared to the Earth about the sun, so we can ignore it. And so what you get is that the angular momentum for the Earth about the sun, you can either calculate it using L equals I omega. I is mass of the Earth times radius between Earth and sun. So this is given, we need mass of the Earth. That turns out to be about 6, a little less than 6 times 10 to the 24. It's 5.98. 10 to the 24 kilograms. All right, this is squared. So I is 5.98 times 10 to the 24 kilograms times 1.496 times 10 to the 11 meters. That number is squared. And then we need to get an omega. So how are we going to get omega? Any ideas? Well, what does omega represent? It represents your angular velocity. But we also determined earlier in our rotational kinematics, uniform circular motion, that angular velocity omega is also equivalent to angular frequency omega. And that is just 2 pi divided by the period. So now that we have a period, we can plug that in here. To get the angular frequency. And so our total angular momentum for the Earth around the Sun is approximately equal to 5.98 times 10 to the 24 kilograms times 1.496 times 10 to the 11 meters squared times the 2 pi divided by 3.153 times 10 to the 7 seconds. So now we plug all that into our calculator. Pi times 5.98 times 1.496. What we end up with is L is equal to 2.66 times 10 to the, let's see here, 24, 25, 22, 27, 27. To the 40. And the units for this are joule times seconds.